Hello students. So we are into chapter 7 and we are studying the frequency response, and today we are going to talk about the Nyquist stability criterion. But in order to understand that, we have to understand something else, okay? Something which is known as mapping or complex mapping. Okay, so first we have to know the mapping. What is mapping? Then we will see there is something called mapping theorem, and from there we will go to the Nyquist stability criterion. Yeah, so complex mapping. Complex mapping is basically like we have a S-plane that we know, right? So we have S-plane and where we say real of S will be here, imaginary of S is here, and we for example root locus we plot here, right? So this is a S-plane, and there is we have for example open loop transfer function. Yeah, so we have some transfer function, say let us say call it GS. Yeah, so S is there, so let us say a point is here, and this which point is that? This point is sigma plus I omega. Let us decide that that's S, right? Okay, corresponding we can plot GS now. Let us say GS is a some function of S, and we are going to plot it here. Yeah, plot it here. Okay, so we can have a function, any function we can have, right? So in first order system, for example, we have 1 over tau s plus 1. Yeah, and accordingly our value is at this point, if s is sigma plus I omega, this value is, we plot real of GS here to here, this is with the imaginary of GS, right? So basically what really means that this point will be simply 1 over tau and the mapping, so we transfer from here to here, so tau sigma plus I omega plus 1. This is what the point, this point is. Yeah, so this is what is mapping, right? So this is the mapping. Yeah, okay, or complex mapping, right? So it's a complex number. So we are drawing here S, we have the S plane, here we have GS plane, right? So we call GS plane here. Yeah, in the Nyquist diagram, for example, what did we do? We actually plotted the G I omega, right? Nyquist diagram, right? Nyquist plot. What we plotted? We plotted G I omega, right? So it was on the, here we had a real of G, imaginary of G, and we changed the omega, accordingly we plotted it. Similar thing is here also, but here this is a formal name called mapping. So here we have mapping from S plane to GS plane. Yeah, why we do? We do because there is some theorem which is called the mapping theorem. The mapping theorem is based on how this moves. Yeah, so let us say this moves. You have decided a path. There could be a path, right? So this path is going like this, coming like this one, goes like this and this, clockwise. Typically we talk about the clockwise. We in the theorem also we mention clockwise only. So let's say this, you are from this point, we are coming here, from here, go like this one. In the complex mapping, the mapping theorem is based on, if you have a function GS And if on the S plane you are going in a loop, then how does this move? Yeah, it will be a loop for sure, because you are starting from here and it has to come back to here, so it will go from here, come back to here. Only thing we don't know whether it will be clockwise or anti-clockwise, and you move one time, how many times, how many loops it make, that we don't know. But this theorem is about that only. So if you move here clockwise, whether it is clockwise here, if you move one time, how many times it is going to make a loop, right? It's closed loop. So if you go from here to here, these are the S value on the path, right? Accordingly, here there will be some way you are going to move this way. This will be maybe from here to here. When you come, you goes from here to here. And then from the second round, it may go like this also. Yeah. So you don't know basically, but so here we can take one example and we will look at that. Okay, so we will have a very simple example, and where we will go through a loop here. We will see how the things are changing here, and we will see some interesting observation. Based on that, we will see this mapping theorem is. So let's have S equal to the GS is equal to 1 over S minus 2. Purposefully I have taken S minus 2 because this will have the value, the root, yeah, on the right hand plane, right? So this will have a pole on the right hand side. So that indicates basically if we make this one as the transfer function, any system which represents this one will be unstable, right? So there is an interesting observation when you have a root on the right hand side, on the right half of the S plane. So this let's understand that. So S, we have a S plane first, right? So S plane here. So S plane is like this. Yeah. So we have like this one. Okay. And here we can plot it here. So we make a cross here like this one, which represents S equal to 2. This is going to be the pole right there. Okay, and let's decide the path, and let's say our path is like this. So we have 1 point here, 1 point here, and 1 point here, 1 point here, 1 point here, 1 point here. So we are going to clockwise. Okay, so 1 point here, then 1 point here, and like that. Okay, so we will start from, let us say we are starting from here. Yeah, we'll go clockwise. We go clockwise. Yeah. And we will see this is our loop decided. We decided. Okay, so this is the S plane, and we want to see how it looks like on the GS plane. So we want to see GS plane, how it looks like. Yeah. Okay, so on the GS plane, we will have something like this one. Okay. Now we have to get the values so that we can plot it here. Okay, so values, so which all so we have real of S this side, and or which is called sigma, and this is a real of imaginary of S, which is omega, right? So we have I omega here, and this side we have sigma, or the real part of S. Now we are going to plot accordingly. Yeah, so plot means we have to find out how the GS here. So what is this point? This point, let us say this is 4. This is point 40, right? 4 plus 0I. This is 4 plus I. This is 4 minus I. This is 2 minus I. This is minus I. This is 0, this is 0 plus 0, right? This is simply 0. Yeah, okay, and this is plus I, simply I, and this one is 2 plus I, and this is how our S is changing. Now if we have GS, then how is GS changing? We can find out here. So we have S, let's write S here, and S we have value starting from here. What do we have? We have 4 plus, just 4 we write here. Okay, so we have 4, start with 4, yeah, then here we say 4, then 4 minus I, then 2 minus I, then minus I, then we have 0, then we have here I, then we have 2 plus I, and then after that we have 4 plus I, and after that we have 4 again, comes back to this one. Okay, so corresponding value or GS will be, since you are mapping, right? So if the value of S is like this one on GS plane, how it looks like? Okay, so 4, so GS will be equal to simply 1 over 4 minus 2 is equal to 1 over 2 equal to 0.5 simply. Yeah, we get that. So we have here mapping. Now second is this one, we have 1 over 4 minus I, right, minus 2. So we get 1 over 2 minus I simply, or we get 2 plus I divided by 5, right? Okay, got that. Now next is 1 over 2 minus I minus 2, which is simply minus 1 over I, right? Okay, and what do we get? Is equal to minus we get simply I equal to I, right? So minus 1 over I, minus 1 is I square, so we get simply I. Okay, now next will be minus I, so we have 1 over minus I minus 2 is equal to minus I plus 2 is equal to, okay, here we have minus, so we can get 2 minus, so minus 2 minus I over 5, yeah, or simply we get minus 2. Okay, so minus 2 plus I over 5. Yeah, okay. 0, when you have 1 over 0 minus 2 equal to minus 0.5. Okay, now I, right, when you have I, 1 over I minus 2, and hence that becomes I plus 2 over 5. So we write like this, 2 plus I rather. Okay, so 2 plus I divided by 5. 2 plus I minus 2 is equal to, yeah, so we get 1 over I, and that becomes minus I simply, right? Okay, then 4 plus I minus 2, that becomes 1 over 2 plus I, that becomes 2 minus I over 5. Yeah, and then 4, we come back to the same thing, right? So we have the same value as this one, and 4 we have 1 over 4 minus 2 is equal to half equal to 0 0.5. Okay, so let us plot it here. So what we will do, this will be the real of GS and this will be imaginary of GS, and we are going to plot it. Yeah. Okay, so for this one we had 0 0.5. Yeah, so we look at this one, we have 0 0.5. What is the maximum we get? Maximum on that axis, we have 2 over 5 is the maximum, 0 0.5 is the maximum, right? So we get 0 0.5. So let us call it, this one is 0 0.5. Yeah. Okay, let's call this 0 0.5. So that we have 1 here, maximum we get. Yeah. Okay. So this is this one is 0 0.5. So you start with 0 0.5. So this is 0 0.5. So we can have a point number also. So let's call this a point 1, 2, 3, 4, or rather A, B, C, D we write. Let's call it A, B, C, D, E, F, G, H, right? A, B, C, D, E, F, G, H. Yeah. So this is point A. So point number we can write it here. This is A, B, C, D, E, F, G, H, A. Yeah. So we have a loop. Okay. So this is 0.5. So this is point number 1. So write A here. Yes. So this is A. Then we have 2 over 5, right, plus I. Okay, so 2 plus, so where do we get? We get here 2 plus 5. Okay, so 2 over 5 we have 0 0.4 basically. So this is 0 0.4, and then you have I over 5. So we get somewhere here, let us say. Yeah. Okay, so this is B point, and what is the value? 2 plus I over 5. Then we have number C is I. So we have I here. So this one. So number C value is I, right? Okay. Then number D, minus 2 over 5 plus I. So minus 2. So this is just opposite of that. Here we have somewhere here. Yeah. Some mirror image of that we get. So let us say it's here. Okay. And this point is minus 2 plus I over 5. And this point is D. So this is D. Okay. Now F, 2 plus I over 5, F. So 2 plus I over 5, and this will be the mirror image of this one. After D we have E, and E is minus 0.5. So this is will have minus 0.5, which will be somewhere here. Let us say here. Yeah. So minus 0.5. Let's write it. So minus 0.5 is the here, and point is E. Okay. And after that, this E is done. Now F. F we have 2 plus I5. Okay, there is something wrong here. F value, when you have I minus, so plus 5. There's some problem here, it should not be like that. So what is the problem? Problem is here 2 minus, so this will be equal to, so this correction, so this will be equal to minus 1 over 2 minus I, which will be equal to minus 2 plus I over 5. Yeah, so minus 2 minus I over 5. So this is the mirror image about this one. Yeah, so real part remains the same. This is as same as D, but mirror image. So it will be here, somewhere here. Yeah, so this point is F. Okay, point F here, and value is minus 2 minus I over 5. Right? Okay. After that, you have minus I. So here, let us say here, this is minus I, and which point is that? This is point G. And then after that, you have 2 minus I over 5. So you have the mirror image of this or this. Yeah. So you will have here somewhere. Yeah. And this is point H. And this is point H is one thing, and the value is 2 minus I over 5. Okay, done. So one thing what you notice is when we are going here clockwise, and here you are going the anti-clockwise, right? So this is the first thing you notice, and you also notice that it completes one round, and here also this is the one closed loop. Here also there is a one closed loop. Yeah, so this one goes, so from here goes here, then from here comes here, from here goes here, then here goes here, and then goes, so but goes in anti-clockwise. Yeah, so goes anti-clockwise. Here it is clockwise, here you get anti-clockwise. So before we see the statement of the mapping theorem, let us see here what is number of zeros here. Yeah? So number of zeros in this case is 0, or Z equal to 0. Right? There is no 0 here, no circle, and number of poles in this was number of poles equal to which is P is equal to 1. Okay. Now number of, when we went through one round around the pole, right? So we have a pole here. We have a pole here, and we are making a complete the path around it. Yeah, closed loop, a complete loop around it. And here we are getting, here it is clockwise, here it is anti-clockwise. Yeah, so number of loops in this case, number of closed the clockwise, number of clockwise loop in GS plane is equal to or is called N is given by Z minus P, in which case 0 is Z and P is 1, so you get minus 1. As per the complex mapping theorem, if you have a rational polynomial, meaning that is the ratio of two polynomials basically, is the GS equal to PS over QS, for example, then if you make a closed loop in a clockwise loop in S plane and corresponding the map of GS, if you draw in GS plane, then number of times this loop will encircle the poles is equal to number of times it is going to make a loop. Number of times it is going to make a loop will be equal to number of times it is going to make a clockwise loop. Number of times it is going to the clockwise loop will be equal to number of zeros inside the original S-plane loop minus number of poles inside the number of minus P, where P is the number of poles inside the original loop, closed loop in the S-plane. Or simply, it tells you number of times in GS plane it is going to encircle the center. Okay, number of clockwise in GS plane, number of clockwise loop encircling zero origin. So encircling origin. Okay, we will come back. Okay, so right now we are just looking at the example. So you just understand this example. We will go more and we will understand more. So I'm going to repeat again. You have this plane here. We have made a complete closed loop, yeah, clockwise, and then we have drawn the map of GS corresponding to this S closed loop. And here we are going to observe how many times this is going to encircle the origin in clockwise direction, and how many times that n is given by z minus p, where z is the number of zeros being encircled by the original loop and p is the number of poles being encircled by the original S loop. And clockwise direction, we get -1. That really means we are getting minus value n equal to -1, means it's not clockwise, it is anti-clockwise. In this case, it is telling me since original S loop has only one pole inside the loop, hence on the GS plane the map encircles only one time because this is 1. But in anti-clockwise way, because we have the sign -1. So -1 means this is not clockwise but anti-clockwise, and only one time. If we had -2, that really means anti-clockwise but 2 times. Okay, we will look at one example in which we will see that is going 2 times. Yeah, we will just, what we will do? We will take GS equal to S minus 2 square. Okay, new GS equal to 1 over S minus 2 square and see what happens. So here we are going to make change. So now our GS is S minus 2 square. So number of zeros are still 0, number of poles are now 2. Okay, so we have 2 now. Okay, and hence number of clockwise loop encircling the origin in GS plane is n equal to g minus p equal to 0 minus 2. We should have -2 now. Means since we have changed the GS to 1 over S minus 2 square, that really means now our mapping should be going anti-clockwise again, but it should, by the time it goes one complete path, we have to here one complete loop, and here it has to go twice. Yeah, so it will go from here, come back, go here, come back. Yeah, so that's what is predicted as per the mapping theorem. Yeah, so we are mapping theorem. Okay. Now, since this value is for 1 over s minus 2, we just have to square it and we get the value, right? Simply, yeah. So this is we are not writing GS here. We will write this value is for 1 over s minus 2, and here somewhere here we will have, I will write in different color. So here we have new GS, right? So we have GS here. Yeah? We are going to write GS here. Okay. Okay. So GS will be equal to 0.25 now. Yeah, 0.5 square of that. Here it will be, we can write 1 over 25. So 25, and then we have 4 minus 1 here, so 3. So 3 plus 4i, right? Okay, 3 plus 4i, here we get equal to minus 1. Here we will get equal to, so we write 25, and then 4 minus so let me write here for corresponding to this one, we have here and that will be minus 2 and like that. So we have 25, and then 4 minus 1, 3, right, and we will have minus 4i, right? Okay, here what do we get? We will get the same value as this one, yeah, square of it. So we get here 0.25 minus 2 plus I over 5. Yet here this and this minus of each other, simply we get square it. So value will be 3 plus 4i over 25. This we get the same. What you see, the repetition, it is making a loop, second loop, right? So first loop was 0.25 to 0.25, and the second loop is just following the same thing. Yeah, so now this one 2 minus I, if you square it, it becomes 3 minus 4i divided by 25, and here it comes back to 0.25. Okay, so if you want to plot it here, how it looks like, so this one was the original 1 over s minus 2. Now what I'm going to plot will be the s minus 2 square. Okay, so here the value, let me plot in black. Okay, so start from here 0.25, so 0.25, so it will be here, let us say this point. Okay, then we have 3 plus 3 over 25 and 4 plus, so we'll have something, let us say it's here like this. Yeah, okay. Okay, now we have minus 1 now. Okay, so I square minus 1, so we have minus 1, so 0.5, so we have something like here, yeah, so okay, and then we have 3 minus, so 3 minus 4i over 25. So mirror image of this one like this one. Yeah. So how we have gone? We have gone something like this. From here, and then from here it went here. Then from here it can come back here, and then from here it has gone here. So it made a loop already. So we started from this point. So this was the A point, this is B, this is C, then this is D. Yeah, then comes back to original. E and A and E are at the same place. So this is E also. E, then this is F as well. The same point is F, and G. This point is G as well. G, and then we have H. This point is H as well. Yeah. So at the same point we have A and E are coinciding. Here's B and F also. Here C and G also, and H and D also. Right. So what you see that this one, this is the black one, is the mapping of 1 over S minus 2 square. And what we see? We are seeing that this is making a loop, but making a loop twice. It has gone from here to here, come back down here to here, come back here, so 2 times. And it was predicted by the mapping theorem. Mapping theorem, what it says? It says that if you have a closed loop in S-plane, and if you map some function Gs, which is of the form of Ps over Qs, where Ps and Qs are 2 polynomial of S, then the number of times the mapped loop is going to encircle origin will be equal to Z minus P. Okay, one thing I did not mention, if you have a S closed loop in the S plane in clockwise direction, then number of times the loop, GS loop, the map GS loop is going to encircle the origin clockwise will be equal to n minus p, will be equal to n minus p, where will be equal to z minus p, where z is the number of zeros encircled by the original S loop, and p is the number of poles encircled by the original S loop. And in this case, you see there is no zeros. In numerator, we don't have any polynomial here, just we have one constant number, and hence the poles are 2 of them because you have a square, and hence 2, so 0 minus p equal to 0 minus 2 equal minus 2. Minus sign indicates that it has anti-clockwise, it will move anti-clockwise, and after that a number indicates how many times it is going to encircle the origin. So this is what the mapping theorem is. It was very important to demonstrate numerically. Okay, based on this one only, we have the Nyquist stability criterion. While plotting this S, remember that it should not pass through any of the zeros, poles and zeros. Yeah, so it has to be away from the poles and zeros, then only it's valid. Now let us say that our GS, we have something not GS, we have some other function which is, let us say, TS. We have TS equal to 1 plus GS. Okay. We have TS equal to 1 plus GS. Then mapping, how is going to change the mapping? This is going to, whatever you have plotted, you just shift the origin. That's it. So the value of GS, whatever you are getting here, we are shifting by 1. Yeah, so 0 here, if you have instead of origin here, if we move the origin here, it will be done, right? So the value, for example, the original value wherever it was 0.5, yeah, will now become 1 plus 0.5, which is equal to 1.5. Hence, that really means we want our 0 will be somewhere here, right? This is 1, let us say it's 1, we are adding 1. So our 0, the axis, we have to move the axis, shift the axis, yeah? This serves as origin for, or this is the origin, okay? This serves as the imaginary axis of TS plane, right? So what we have done? This is the map of 1 over S over S minus 2. Then we made it a square. Then we have the map like this one. Now let us say we want to have for a function, we want to map it. How will we map? Our function is Ts equal to 1 plus Gs. And how? Why we are saying that? Because we have a transfer function, closed loop transfer function R. Typically we have denominator, we have 1 plus open loop transfer function. So this is open loop T naught S, we call it T naught S, right? So T naught S, right? This is like this, it's not open loop. Open loop is GS. This is like a denominator of the closed loop system, right? So we have BBN studying, right? So we have the closed the closed loop transfer function will be equal to GS divided by 1 plus GS for the unit feedback loop, right? Unit negative feedback loop. So 1 plus GS comes here, right? So we want to look at also the what is the relevance to the closed loop system, and hence closed loop for in order to find out the relevance, closed loop system will look like 1 plus GS, where GS is the open loop transfer function. So we want to know how does the mapping looks like for the closed loop system, and for that 1 plus GS, mapping of 1 plus GS is important. And how can we do it? Just you add 1 to the value, right? So 0.15 becomes 1.25. This becomes 0, for example, now, right? And so on. We just add 1 to all of them and you get the TS value. Or simply you move the origin, right, from here to here, or move the imaginary axis by 1 unit. Yeah? Move to the left so that the original 0 becomes 1 now, and this is the new origin for TS, right? So hence this becomes 1, this becomes 1.5 and so on, right? So what you see here, that now instead of circling 0, it is circling 1, right? Given this background in mapping theorem, now you should be able to understand the Nyquist stability criterion. So we will study that now. Now, since we have learned the complex mapping, now we should be able to apply to the stability criteria, which is known as Nyquist stability criterion. Okay, so Nyquist stability criterion, and what it does, it is whatever we studied, we just the inverse of that, reverse of that. So what is the meaning of that? So for example, we had there GS 1 plus GS we are talking about, right? We had first GS, then we added something, and then based on that we try to find out how the mapping looked like. What about now we are interested in now the closed loop, right? And for closed loop characteristic function, the equation is 1 plus GS times HS, right? Okay. Closed loop, this equal to 0 basically, yeah, and that really means that there will be some shift of axis, yeah. So let us see. So if you look at the mapping, so let's see if there's a S plane, right? So we have S plane. Let us say we are going clockwise like this. Then there will be corresponding 1 plus GS plane. Yeah, so we have GS plane. 1 plus GS times HS plane. Okay. Let us say this plane looks like this. Yeah. So number of here, depending on how many the poles and zeros are there, we can have the number of loops n equal to z minus p times it is going to go encircle 0. Mind it is going to encircle 0. Okay, meaning of what? Number of times. This is the 1 plus GS plane, right? Meaning that we are talking about now P and Z for the closed loop system. Right? So if P is the number of poles for the closed loop system, if Z is the number of zeros for the closed loop system, then number of times this is going to encircle zeros in clockwise direction will be equal to n minus z minus p, where p is the number of poles inside this contour and z is the number of zeros inside this contour. Now let us say we extend that. Now if you want to look at GS times HS plane now. Yeah. Now in this case what happens? We are going to just shift what? We are just going to add -1 to this and we get that. So whatever is 0 here, we are going to shift these to here, right? We have to go forward, right? Go like this one. So that now 0 becomes -1. So that when you have -1 this, +1 becomes 0. So we have the new system which will be like this. And where this point becomes O dash, so we have O dash here. And accordingly, it will go something like this. Right? So here we have new 0 and whatever the original O was will be here. And what is the value? Original O now becomes -1. This in new system, the value is -1 for this one. Yeah? Okay, so here -1 plus 0j, you can say plus 0j, right? 0i, -1 plus 0i. This point is -1 plus 0i, right? Okay. Now, here from the mapping theorem, what it tells you, depending on how many times you have this loops, number of encirclement of 0 is going to give you the number of poles and zero inside this S plane. Now, if you have just HS and GS times HS plane only, you are not adding 1 only, right? You are not adding 1. Then what happens? Then you will have the same cheese, the same thing, but shifted to the right. Yeah. So shifted to the right means basically you have the original 1 becomes 0 now. Yeah. So that original 0 becomes -1 now. So encirclement of 0 is equivalent to encirclement of -1. So we just write 0 becomes 0 plus I0, right, is equivalent to, in this case, becomes encirclement of point -1 plus 0I. Yeah. We have just shifted. So what we are saying now, this is open loop. Right? We are going backward, given the closed loop poles, right? And we are, so given the, we are going to predict basically. Okay, the idea is reverse, as I said earlier. Here we will look at the open loop GS-HS plane, and we are going to see the map. And we will see how is this, some curve, yeah, some map is encircling a point -1, that will give us some idea how many zeros and poles are there on the S plane. How many zeros and poles of the closed loop system is there. That we can guess based on that. That's the deal. That's what is the Nyquist stability criterion. Finally, we have to find out how this is behaving, right? We have to find out whether we have to make sure that open loop transfer function doesn't have any zeros and poles on the right S plane. And how we can guarantee? We have to take a very big infinite, actually we have to have a loop or contour such that it encompasses the whole positive S plane. And then we are going to have the 1 plus GS times HS plane. We will plot that, map of that, and then from there we will -1 to this and we will get GS and HS plane. This GS HS plane is nothing but open loop plane, basically the transfer function, it is corresponds to the open loop transfer function. And here, if originally we had a number of poles and zeros, number of times it is going to encircle point -1 will be reflected. Okay, but for us this will be given and we have to predict. The Nyquist criterion is given this, then how many poles are there, how many zeros are there. Actually how many poles, zeros are difficult to find individually, but we will be able to find Z minus P, the difference between the two, which is important. So then we look at the open loop transfer function. For open loop transfer function, we are going to just for some S, infinite S, meaning that what we take typically is a semicircle. Yeah, so in the S plane, you take a semicircle of infinite radius, and this will automatically make sure that whole of the positive S plane is covered by it. Once you have taken that, then, and for this if you plot, you forget this now, go directly from here to here. Based on this, you plot the open loop transfer function here, simply, right? Okay, and then you check how it looks like, whether it goes clockwise or anti-clockwise. Here you are going clockwise only. Yeah, so how you are going, this will be infinity. Here this will be a point where it will be the imaginary axis. So this will be 0 minus infinity I. This will be 0, 0. This will be 0 plus infinity I. In between, this will be some value you are going, I omega basically is changing. And here there will be some, on this we are assuming that the value of this is finite. It will not be infinite, some finite value, but the same value. We will look at that later. Now this, so what we are doing, we are skipping this one. We have the S plane, and we have this contour which is very infinite, semicircle one, so that we cover all of the right S plane, so that we capture all the unknowns, zeros and poles. Yeah, and then what we do, we go here and just map it here without knowing whether there is a pole or not. We don't care. We just map it. We just what you do, you plot. What you plot? Real of GH here and imaginary of GH here. That's it. And you plot it like the polar plot, yeah, or Nyquist plot, right? We said Nyquist plot. Nyquist plot because of some reason. Okay, now just look at how many times it is going to encircle point -1 plus 0. I will tell you some information about how many poles and zeros of the closed loop system lies within this, or that really means on the right S plane. And this is all about the Nyquist stability criterion. Remember that we have to assume that a GS limit S tend to infinity 1 plus GS plus HS equal to finite, or you can also write GS times HS equal to a constant or finite number, a finite number. Okay, and when will it happen? Typically when, that's why one of the things you remember, we had n less than the greater than equal to m condition. Here it is the order of the numerator is m and order of the denominator is n. So if n is bigger to m, we automatically will have more s here, less. If n is bigger, strictly n is bigger than m, you have more s here, less s here. Hence s tend to infinity, automatically make this the whole thing equal to 0. So you get a 0 value. If both n and n equal to m, then you get a constant value, right? You get a constant value, and that will be valid for all of them, right? So that constant value will be everywhere. You go like either this point, this point, this point, this point, everywhere you will get the same constant value. If you get the same constant value for all the points starting from here to there, that really means these 2 points will be represented by a single point somewhere. Let us say that point will be some point. Let us say you have this point or this point. Let us say this point will be the entire from here to here. So let's call it A, somewhere point B is there, C and O, like this one, right? So this point will represent only one value, and that will be equal to A, represent A, B, C. The whole path will have a single value which will be here. All others will be from C to A. So all others from here to here will be equal to, this will be COA. All of them. Yeah. What you get interesting about that, if you are going from here to here, this is nothing but simply the plot will be of G. This is I omega only, right? Sigma equal to 0, I omega. So this becomes GS, HS becomes equal to G I omega times H I omega, right? And then you are going to plot, you are going to change omega from minus infinity to plus infinity, and this, and you are going to plot here, and that plot is what you call, you studied yesterday, you call it Nyquist plot. Or simply what it tells you that you just have a Nyquist plot and see how many times the Nyquist plot is encircling point -1, and that will tell you that n will tell you the difference between number of poles and number of zeros of the closed loop system which are lying on the right side of the S-plane. Means it will tell you whether the system is stable or not, simply. Let us understand this with some example, the same example that we took to understand the complex mapping. Okay. So our example was, we took GS, okay, now GS equal to 1 over S minus 2, right? So let's instead of GS, let's call it GS times HS, right? We can see the limits now. So limit, for example, S tends to infinity, GS HS will be equal to limit S tends to infinity, and you can put here S minus 2, and that you will get equal to 1 over infinity, which is equal to 0 only, right? We are getting 0. Okay, so in fact you can draw a the contour, right? This is R, which is infinity. You can take in that, if this infinity, that really means is even on this one, what happens at this point also, if you look at this, then you have a J infinity, right? Or simply we say I infinity. So even we can put limit S tend to infinity. That really means we can just put here and see what happens. We can corresponding to this point 1, we will have I infinity, then minus 2, right? Or simply equal to 2 minus I infinity. Yes. Okay, so that is will be equal to 2 plus I infinity over 4 plus infinity square, or 2 plus 4 plus infinity square plus I infinity 4 plus infinity square, and you know that this will be 0, and this here, this is bigger than this one, 0 plus I 0, simply you get 0. Yeah, so regardless of which point you go, everywhere the value will be 0 only. That's what it tells you. We will simply write that here the value of value of GS HS equal to 0 for the entire, you see, clockwise, right? For the entire loop it's like that. Here we don't know, so here this value is minus I infinity, this is I infinity, and we are going to see GS HS plane, or simply we have to draw the Nyquist plot, right? So we have to from here to here, everywhere the value is 0, so of course value is 0 here and here also, only we have to see how it is here, right? So if we go here, right, what do we find? We have this is infinity here. For any point on this line we have I omega, and hence we have GS Gi omega times Hi omega will be equal to 1 over I omega minus 2, or equal to 1 over minus 2 plus I omega is equal to minus 2 minus I omega divided by 4 plus omega square, right? Okay, and then what we have to plot is minus 2 over 4 plus omega square minus I omega over 4 plus omega square. That's what we need to plot. Roughly you can find out the values. Yeah, so what is the values? So we can write here Gi omega times Hi omega, and the value when omega equal to 0, and then what do we get? We get minus 2 over 4. Yes, 0, so we get simply minus 0.5 that we are getting. Yeah, from here minus 2 over 4, 0, and minus, here we get a minus I 0 over 0 also. And what is the angle? Okay, angle we get tan inverse 0 over this value minus 0.5. So tan inverse this is minus tan inverse we get omega over 2 basically, and that, right, omega tends to 0, so 0 degree, so you get simply minus 0.5 0 degree. Yeah, so that we get one side. When omega equal to infinity, that then we get value 0, and so tan inverse and this omega divided by this one, so omega over 2 basically, where omega tends to infinity, which is positive so this is infinity, so simply you get is equal to 0, and value is 90 degree, right? So 0 degree, 90 degree, we are getting like that. In between, when you have omega equal to when omega equal to 4, right? So then what happens? Or omega equal to 2, then we have, so omega equal to 2, and then what happens? Then we have omega equal to 2, so 2 to 4, 4 for 8, so you get minus 2 over 8 minus I and 2 over 8. Yeah, so right, that's what you get. That really means we can write in terms of its the radius basically, and the radius will be, the value will be 1 over 4 plus omega square, which is 4, square root of that, and tan inverse. Now both the things becomes the same at that point, so tan inverse 1, which becomes 45 degree. So what we get is simply equal to 1 over root 8, so 2 root 2 tan inverse or angle is 45 degree, right? So this we can plot. So omega equal to 0, then we have 0.5 and angle is 0, so this is minus 0.5, right? So we have minus 0.5. So here we have minus 0.5. So we have minus, say, minus 0.5. No, okay, so we made a mistake here. You see, here minus, we have minus, so we are talking about the where sine and cos both are minus. And when is that possible? So that will be the both are minus, that will be third quadrant, right? So for example, sine will be 0 here, sine will be 0 here, then plus 1 here, 0 here, and minus here. Cos will be 1 positive here, 0 here, negative here, and then 0 here. So both sine and cos, both negative, are in third quadrant. So that really means here it was supposed to be the magnitude, you know, so we cannot write like that. If we get the value g I omega times h I omega equal to minus 0.5, that really means this is 0.5 and tan minus omega minus divided by minus 2, so you have to be careful, and so magnitude remains 0.5 but angle is 180 degree. Yeah, so both are this omega but very a small negative value only, so both of them have value negative here, so it will be tends to 0 but from negative side, so 100, this will be point very close to that line, so it will be 180 degree. Okay, so now omega equal to infinity, the same here. What you get is both of them are negative only. We can assume omega, we are plotting for 0 to omega, so positive values. So we have sine and cos both negative values, and hence we have 0, but this will be, we can write like this, equal to minus tan inverse minus omega minus infinity divided by minus 2, and hence will be minus 90 degree. Okay, so we have minus 90 degree, yeah, or you can call it minus or minus 180 degree, right? Since we are calling this minus 90 degree. Okay, and now omega equal to 2, we have like this one only, but tan inverse we can say minus 2 over minus 2, yeah, so we get 1 over 2 root 2, not 45 degree, will be here, we are going to in between here, so this will be like this one, yeah, so we are going to get 100, this is minus 90 and 45 is minus 35 degree. Okay, so this is minus 135 degree. Okay, so this is the correct values. So let's plot this one. So we have 0.5 here, this is a polar plot, so no negative value. So we have 0.5 and at 180 or minus 180 degrees, so we are here. Then next is omega equal to 2, which is this value, so less than 0.5, and minus, so on this angle, yeah, so we have on this one, so let's keep this a little away, so let's call this is 0.5, so this will be somewhere here, so if this is 0.5 and this one is 0.5, so this is the point which will represent this, So this is 1 over 2 root 2. Okay, and then at omega equal to infinity, at omega to infinity we have value 0. Yeah, and value 0 at minus 90 degree. Yeah, so we are going here somewhere. Yeah, so this will go something like this. Yeah, like this. So let's try it. What I mean to say is it is going to be something like this. What we see that this is going clockwise, the anti-clockwise, right? So it has gone from, no, we have to go from minus infinity to the, or here you have to go 0 to infinity, right? So we are going 0 to infinity, of course. So this is going anti-clockwise. So 0 to I infinity. So 0 to, this is omega equal to 0. This is omega equal to 2, and this is omega equal to I infinity. Right? We take the from here to here now. So from here to here will be at the same point as 0. Right? So regardless of which point you are, it will be the 0 only. So we have the 0, this one, and from here we have gone here. Here the value will remain the same at 0 only, and then the value is also here omega and minus I omega both the same value here, and then we will, when we move, we will be making half circle again. So it will be something like this again. Yeah, so okay, and this is 0.5. So clearly what you see, this is a full circle. This is the mapping of that, right? So it has been mapped here. So this is Z S H S plane now, and our minus 1, this is 0.5. So basically minus 0.5 actually, right? So minus 1 will be somewhere here. This is minus 1 plus I0. So this is outside, right? So this is what we see here. This is not encircling minus 1 actually, right? So that means the value, what is the value? First of all, anti-clockwise we understand, but the thing is, this point is not inside that, and hence it tells you that simply tells you n equal to z minus p equal to 0, because GSHS did not encircle minus 1 plus I0. Yeah, and how? Yeah, n equal to GS equal to 0, because closed loop, right? Closed loop n equal to G minus P equal to 0, because it is not so. So what is the closed loop? If you look at this closed loop here is 1 plus GS plus times HS is nothing but 1 plus 1 over S minus 2 is equal to, what do we get? We get S minus 1 over S minus 2. That means what? That tells you that S Z equal to 1 and you have P is also equal to 1. Hence n equal to Z minus P equal to 1 minus 1 equal to 0. Hence it tells you it is not going to encircle, right? So this is what it is not going to encircle minus 1 point, minus 1 point on the GSHS plane, and hence it is not encircling this point. Yeah. Hence, what you come to know from here, that the number of zeros and poles are the same, basically. That's what it tells you.